Hi everyone, welcome to our online classes. Today we will discuss the portion Fourier transform that we have already covered. And in this class, we will discuss two important problems related to Fourier transform. Planning this as an interactive session, so you can ask doubts at the end of the class. Also, some exercise questions will be given, and you have to do it as a classwork and upload the answers to Google Classroom. If fx is an absolutely integrable real valued function, that is, if integral minus into infinity mod of x is less than infinity and is piecewise smooth on any finite interval, the Fourier transform of fx is defined as f omega equal to 1 by root 2 pi integral minus into infinity fx e raised to minus I omega x dx. And the inverse Fourier transform small fx equal to 1 by root 2 pi integral minus into infinity f omega e raised to I omega x d omega. If fx is discontinuous at x, the left-hand side of the above equation is replaced by half of f of x plus 0 plus f of x minus 0. That is, the average of right-hand limit and left-hand limit at the discontinuity point say x. If fx is continuous at x, the integral representation and the function will give the same output. Special cases. When fx is an even function, Fourier transform is given by fc omega equal to square root of 2 by pi integral 0 to infinity fx cos omega x dx, and the inverse transform small fx equal to square root of 2 by pi integral 0 to infinity fc omega cos omega x d omega. When fx is an odd function, Fourier transform is given by fs omega equal to square root of 2 by pi integral 0 to infinity fx sin omega x dx, and the inverse transform small fx equal to square root of 2 by pi integral 0 to infinity fs omega sin omega x d omega. Come to the problem. Find the Fourier transform of fx is equal to x if mod x less than a and equal to 0 if mod x greater than a. And what is the nature of the function fx equal to x if mod x less than a and equal to 0 if mod x greater than a? See, from minus a to a, fx equal to x, that is identity function, and equal to 0 otherwise. See, the entire range, we can split this entire range as minus infinity to minus a, then minus a to 0, 0 to a, and a to infinity. See, the function has non-zero values within the range minus a to a and equal to 0 otherwise. And what is the nature of the function fx equal to x in mod x less than a? And clearly this function is an odd function. That is, fx is an odd function. Fx equal to x is an odd function in the range minus a to plus a. Since this function fx equal to x is an odd function in minus a to a, its Fourier transform is equivalent to minus I times the Fourier sine transform, because we are computing the complex Fourier transform. That is, f of fx is equal to minus I into fs of omega, where fs omega is the Fourier sine transform. See, we are multiplying this fs omega with the minus I because Fourier, we know that Fourier sine transform and Fourier cosine transform are always real numbers. And because this Fourier transform is always a complex number, so we are multiplying this Fourier sine transform with the minus I. Where this fs omega is the Fourier sine transform, and it is equal to, what is the formula for Fourier sine transform? It is equal to square root of 2 by pi integral 0 to infinity fx into sin omega x dx. So this is the formula for computation of Fourier sine transform. And remember that this Fourier sine transform is always a real number. This is equal to square root of 2 by pi integral 0 to infinity. Integral 0 to infinity, we can split the 0 to a and a to infinity. From the range 0 to a, we have the output fx equal to x, and after that the value is 0. So this is integral 0 to a, we are replacing fx by x, and fx sin x omega dx, and after that the value becomes 0 because the function has output. This is equal to square root of 2 by pi. Applying integration by parts for the product x sin omega x, that is, the first function x into integral of sin omega x, that is minus cos omega x divided by omega minus derivative of this first function 1 into derivative of this minus cos omega x by omega again, that is minus sin omega x divided by omega square, then plus derivative of this 1 is 0, and the entire expression is evaluated from 0 to a. This expression, that is square root of 2 by pi, first term minus x cos omega x by omega plus sin omega x by omega square, and evaluating from 0 to a. Now substituting limits, that is equal to square root of 2 by pi, upper limit. In upper limit we are replacing every integration variable x by a, that is minus a into cos a omega divided by omega plus sin a omega by omega square. So this is the upper limit. And in lower limit we are replacing every x by 0. So the first term 0 because multiplication with x, and second term is also 0 because sin 0 is 0. So in lower limit we have 0 equal to square root of 2 by pi minus a omega, that is minus equal to square root of 2 by pi minus a cos a omega by omega plus sin a omega by omega square, or we can take LCM, that is square root of 2 by pi minus a omega cos a omega plus sin a omega the whole divided by omega square. So this is hence the required Fourier transform or the complex Fourier transform capital F of fx is equal to minus I into the Fourier sine transform. So we are multiplying this entire quantity with the minus I. So this is equal to I into square root of 2 by pi, I into square root of 2 by pi. So minus into minus, the first term is plus, that is a omega cos a omega divided that is equal to minus I into equal to minus I into square root of 2 by pi minus a omega cos a omega plus sin a omega the whole divided by omega square, or we can multiply with this minus 1 and the final answer will be I into square root of 2 by pi a omega cos a omega minus sin a omega the whole divided by omega square. So this is required Fourier transform or required. Now come to the second Fourier transform. Express fx equal to half for 0 less than x less than pi equal to 0 for x greater than pi as a Fourier sine integral, and hence show that integral 0 to infinity 1 minus cos pi omega by omega sin omega x d omega equal to pi by 2 for 0 less than x less than pi and 0 for x greater than pi. And because we are required to compute the Fourier sine integral, we will first of all compute the Fourier sine transform. So as before, we have the Fourier sine transform fs omega equal to square root of 2 by pi integral 0 to infinity fx into sin omega x dx is equal to square root of 2 by pi. See, the function is defined 1 by 2. The function is defined as 1 by 2 for 0 to pi and after that 0. So the integration becomes integral 0 to pi. For fx we replace this by 1 by 2 into sin omega x dx, and after that means for x greater than pi the value of function becomes 0. So the entire integral becomes 0 equal to square root of 2 by pi 1 by 2 into integral of sin omega x dx, that is minus cos omega x divided by omega within the limit 0 to pi. So this becomes minus 1 by square root of 2 pi cos omega x divided by omega from 0 to pi. So the balance answer equal to minus 1 by square root of 2 pi, upper limit replacing x by pi, that is cos pi omega minus cos 0, that is 1 the whole divided by omega, or this is equal to 1 by square root of 2 pi 1 minus cos pi omega divided by omega. So this is the required Fourier sine transform. That is, the Fourier sine transform fs omega is equal to 1 by square root of 2 pi 1 minus cos pi omega the whole divided by omega. Now in order to derive the integral, we have to invert this function. That means the inverse Fourier sine transform. The inverse Fourier sine transform by definition it is square root of 2 by pi integral 0 to infinity the Fourier sine transform fs omega into sine omega x d omega equal to square root of 2 by pi integral 0 to infinity 1 by root 2 pi 1 minus cos pi omega 1 minus cos pi omega divided by omega into sin omega x d omega. On simplification, we can cancel one root with this 1 by root 2 pi, and root pi into root pi becomes pi. So this is 1 by pi integral 0 to infinity 1 minus cos pi omega divided by omega into sin omega x d omega. So this is the inverse Fourier transform, or the integral representation of the given function fx. And see, the right hand side Fourier integral converges to fx at all continuity points of fx, and at discontinuity points of fx this right hand side Fourier integral converges to average of left limit and right limit. That is the Fourier integral representation. Fx is equal to 1 by pi integral 0 to infinity 1 minus cos pi omega by omega sin omega x d omega, and this expression is valid for x not equal to pi, because x equal to pi is a discontinuity point. At all continuity point the right hand side Fourier integral converges to fx, and but in our question we are required to evaluate integral 0 to infinity 1 minus cos pi omega by omega sin omega x d omega except for x equal to pi. So we are deriving, we are simplifying this integral, or integral 0 to infinity 1 minus cos pi omega divided by omega sin omega x d omega equal to pi into fx for x not equal to pi. This function as pi by 2. This answer is pi by 2 for 0 less than x less than pi and 0 for x greater than pi. So this is the required answer, but one point is missing. That means at x equal to pi, and at x equal to pi what will be the value of this right hand left hand side integral? This integral will converge to pi into half of f of pi plus 0 plus pi minus 0, and pi plus 0, that means the right limit of pi is 0 and the left limit of pi is 1 by 2, and the average value is 1 by 2 plus 0 divided by 2, that is 1 by 4. So at x equal to pi the function, the integral value is equal to pi by 4, but it is not recorded in the question, so we are only simplifying the integral value for x not equal to pi.